Hi, everyone. Thanks for attending another one of our machine learning lunch seminars. Today, we're excited to host Hua Wei. He's an assistant professor in the Department of Informatics at New Jersey Institute of Technology. He received his Ph.D. at Penn State University. Research generally in the areas of reinforcement learning, data mining, urban computing, has won awards such as the Best Applied Data Science paper at ECML-PKDD 2020. Research currently being funded by the DOE and NSF, and excited today to have a presentation on the decision-making in the real world, such as reinforcement learning for traffic signal control. So thanks.
Okay. Thanks, Tyler, for the nice introduction. Hello, everyone. Nice to meet you guys. My name is Hua Wei, and today I'm going to talk about our work on towards actionable decision-making in the real world. So this is the map of Manhattan. Here you can see the Manhattan. And our campus, like NJIT, have two campuses. One is in New York here, and one is in Jersey City. And my background is an exact view from our Jersey City campus. You can see the Manhattan Island clearly. So if you ever come to New York, feel free to drop me a message on Twitter or something, like drop me an email, we can talk. So I got my PhD from Pennsylvania State University from 2017 to 2020. And my research interest, as Tyler introduced, is reinforcement learning, data mining, and urban computing. So before I dive into the talk, I'd like to raise a very general question. That is, why do we need intelligence? So to answer this question, we might ask a few people, like the experts who know intelligence well. Maybe psychological people, they are better than us to answer this question. So psychologists define the intelligence as the three aspects: the ability to recognize problems, the ability to learn, and the ability to solve problems. Similarly, in data mining or in machine learning, we also have this similar steps. Say we have descriptive analytics, which deals with what happens in the past, and predictive analytics deals with we try to predict what will happen in the future, and prescriptive analytics, which tries to answer the question that how can we solve the problem in the future, or how can we make things happen in the future. And the neurologists also believe that we have brain for one reason only, that is to produce adaptable and complex movements. And they said the movement is the only way we have to affect the world around us. And similar to this claim, the professor in UC Berkeley, Sergey Levin, he also made a claim that we need machine learning for one reason, and for one reason only, that is to produce adaptable, complex decisions. Using this three steps or three analytics in data mining as an example, so we can see the pedestrian recognition is one of the famous or one of the classical descriptive analytics in CV. And trajectory prediction is also another useful or very fundamental research in predictive analytics. But these two, after identifying the pedestrians and after predicting the trajectories of pedestrians, that is not the end. The very end of these two research is try to help our humans to, or help the machines to decide, make a decision, how can we steer our cars, right? So you can see the two analytics, descriptive and predictive, they are both beneficial for the very last analytics, the prescriptive analytics. And this very last step of prescriptive analytics is very valuable. And of course, it's very difficult, much more difficult than the previous two analytics. Speaking of the decision-making, in the urban system, we think about the bigger scope, not just the pedestrians or autonomous vehicles. We also have three stats, three analytics. The descriptive analytics, trying to describe, as I said, trying to describe what happened in the past. One classical task would be given a sampled or sparse data. How can we impute the data to understand the past better? And another task on predictive analytics could be the traffic prediction. Given the past few time steps would we want to predict how many cars or how much vehicles on the road in the next few time steps. And the last one and very important one is the prescriptive analytics. And in this talk, we're going to talk about the traffic signal control, which aims to optimize the traffic movements or the speed of the whole city, or we want to optimize for certain vehicles. Say here in this example, we want to optimize the ambulance to achieve to their destination as soon as possible, as fast as possible. Before we dive into the traffic signal control task, maybe we can discuss a little bit why artificial intelligence or reinforcement learning or data mining could be beneficial to this task, right? So here, if you ask this question, why AI would work, and people usually say, now we have big data, or now we have high capacity models. That's the reason why machine learning or data mining works currently. Speaking of the high capacity models, then reinforcement learning is considered one of the most one of the high capacity models that can solve the very complex decision-making tasks. You will see Atari games, and you'll see the reinforcement learning can tackle the game scenario or the robotic scenario. And using this reinforcement learning method, we can also control the traffic signals. So if you're not familiar with reinforcement learning, I can give you a brief, very brief introduction here. So in traffic signal control or in reinforcement learning, we have an agent, the small robot here. We want to help this robot to learn better, to make better decisions. And the goal of the traffic signal control problem is to take actions to minimize the travel time of all the vehicles. And the small robots will observe the whole traffic state at time step T, and it will take actions. This action will be fed into an environment. And after feeding into the environment will tell this robot on how good and how bad your current action is. So you can see the state could be a feature representation of the environment, and the action is the robot's output to the environment. It could be in traffic signal control problem, it could be like the red light on the Western Avenue or the green light on the Western Avenue, right? And then the environment will also give you a reward. The reward is a scalar feedback signal telling this robot how good and how bad your previous action is given on this observation, right? So here, say at this time step, we have the robot observe that there are one car waiting on the Western Avenue and two cars incoming. But if we define our state as equivalence on the road, so it could be 0, 0, 1, 0, because there's only one car waiting here, right? So all the other incoming directions are 0. The equivalence on the incoming directions are 0. And then this agent say, okay, I can keep or I can change the current traffic signal. What should I do? Maybe at first he said, okay, I'm gonna keep this red light on the horizontal or on the Western Avenue. What would happen? Say maybe 5 or 10 seconds later, there are 2 more cars waiting on the road, right? So the environment is telling you, okay, you're making this traffic condition worse. So it's getting more congested. And this agent will say, okay, this is a bad action. Maybe I should take next time when I'm facing the same situation, I should change. I should take the action of change. So here, if we change these traffic signals from red to green on the Western Avenue, then all cars can move smoothly, right? And then the reward could be you are making the traffic situation less congested. So in this trial and error approach, the agent could learn how to take the better action in different situations. So compared to the transportation methods, which usually solve this problem as an optimization problem, they want to minimize the travel time. And with regard to some pre-assumed traffic model, the traffic model could be the cars are coming uniformly, and the cars could stop and go with the full speed. And given this, by solving this optimization problem, they could have a closed form solution. Like the signal plan could be how many green lights, how many seconds of green lights in certain direction. So you can see that after this function is learned, it should be static. It should not be really changes a lot to the current traffic situation. And it also have a strong assumptions on the traffic model. As I mentioned, the cars come uniformly, which is not realistic in the real world. So in contrast, the reinforcement learning method does not assume the traffic model, right? So the function is learned, it has little assumptions on the traffic. Now you can see that the reinforcement learning agent could have a better performance if the traffic are complex, right? But there is one challenge here in traffic signal control. That is, how do we define these feedbacks? You can think of in traditional transportation, they have minimize the goal is to minimize the travel time. And in reinforcement learning, if you want to also consider it as a optimization problem, you should define your feedbacks in order to make the final results. You are optimizing the travel time. So in our very first paper, in using deep reinforcement learning for traffic signal control, we define our reward as the weighted sum of queue length, waiting time, and delay. But as I mentioned earlier, that the only objective in traffic signal control in classical transportation method, they are only minimizing the travel time of cars. But this we are trying to understand, is this weighted sum of the reward in the final results still optimizing towards the travel time of cars? Actually, the travel time of cars is infected by a lot of factors. Say the traffic signals could be one factor influencing the travel time, and the free moving speed or the free moving of the vehicles could also influence its travel time. So directly optimize this travel time is hard, but like this weighted sum lacks of theoretical justification whether optimize this reward could be towards minimizing the travel time of all the vehicles. So later in our two papers, we proved that if we define the reward as queue length for each single intersection, you are optimizing towards the travel time of cars. And for later in KDD 2019, we further proved that if you want to coordinate all not just for one single intersection, if you want to coordinate the intersections, you should define your reward as pressure. So I'll give you an example here. So if you have a single intersection, you should not define your reward as we did in 2018 KDD paper. You should not define that with the sum of queue length, average travel time, or sum of delay. You should instead define that as queue length. So here in this example, you can see if we have a single intersection and the traffic is uniform, and this formula method has the better results because it's the closed form solution from transportation. And you can see the simple reward in reinforcement learning gets the better performance than the complex reward, and it has the similar performance with the formula method. So this is the travel time, average travel time, and the lower the better. And but in real world traffic, like when the traffic is no longer uniform, you can see that the formula method performs worse than the reinforcement learning method, even though it's defined in complex reward. But with simpler reward, the reinforcement learning could also achieve better, right? So this is just a single intersection situation. But in traffic signal control, you definitely need to consider the traffic signals along the road, or you have multiple traffic signals, you want to coordinate them. How do you define your reward? And then in the 2019 paper, KDD paper, we proved that if you define your reward as the pressure of the intersection, you are actually maximizing the system's throughput by minimizing the pressure of each single intersection. So the pressure idea is like this. So here in this north to south direction, the pressure could be defined as the number of incoming vehicles minus the number of cars on the outgoing lanes. So here you have 4 cars incoming, 1 car outgoing, then you have the pressure for this direction is 3. And in this horizontal direction, the pressure is similarly 1. So the traffic signals would give the pressure, they would give green lights to the directions that have higher pressure. So here, since this direction, the vertical direction have higher pressure, then that give them a green light. But in the right-hand example here, you can see the vertical direction has a pressure of -2. The horizontal direction has a pressure of 1, and then this horizontal direction should be given a green light, right? So you can see here the 4 cars are fully congesting this downstream road. So you should not push more cars into this direction, into your downstream intersections to make them more congested, right? So this is the idea of the pressure, and using the pressure, we can achieve the closed form solutions in traffic signal control. So here we have 4 intersections along a corridor, and usually in traffic signal control traditional methods, they would like to form a green wave. So the green wave is basically says once the cars passing through the first intersection will never be stopped by the following intersections. So here we can see the traffic signals, reinforcement learning controlled traffic signals are still learning, but after 3,000 steps, the green wave is learned by here. If you take a look at the first vehicle here, will never be stopped by the following up vehicles. So this is also you will experience in Manhattan if you drive along a one-directional traffic. So this is a work that I did before I was an assistant professor, and that was during my PhD. So in the early days of my PhD, my group had been focusing on reinforcement learning for traffic signal control. We started from the very first step using reinforcement learning for traffic signal control, and then provide theoretical proof on the best reward design, single intersection, and move on to the multiple intersections. And then later, our final result could be controlling or coordinating the citywide traffic signals, which has about 2,000 intersections in the whole city. So this is one intersection, single intersection. This is a demo I already showed you. And in the final project, the end of the project, we have this about 2,000 traffic signals coordinated in New York, Manhattan. So after proving that reinforcement learning could work in the ideal case, all those kind of environments are done in simulations. After proving the reinforcement learning agents could be applicable in the simulation and it could have better results than the traditional methods, then our motivating questions is that since now we have this reinforcement learning model worked, right? Does it work in the practice? And this motivates us to take a step back. We wanted to work in the practice. And if we investigated how the successful applications of reinforcement learning, we would notice that the current reinforcement learning methods, they mostly be successful in the simulation or in the game area or in the artificial area, like the Go game or the robotics simulator or the complex game. But in order to make it to the real world, there is a challenge here. That is, we do not have the realistic simulator. So on the left-hand side, this is a simulator we used and we developed for traffic signal control problem. And this is what we see, the camera, the screenshots of the real world camera in the real world. So you can see there's a lot of differences between them. And actually this no realistic simulator challenge is not just for traffic signal control. They could happen in any real world complex systems. Say in the weather prediction, the hurricane prediction task, this is the predicted trajectory, and the green is the predicted trajectory, and the red trajectory is the real trajectory of the hurricane. We could also have this prediction versus the simulator versus the reality challenge. And so that motivates us to focus our work on the next step, that is to build a more realistic simulator. So this is also funded by the NSF currently, we are focusing on building a simulator that is learned from the real world data. So that is called learn to simulate. Actually, a good simulator can not only serve as a test bed for reinforcement learning, it could also be beneficial for many other applications. Maybe we could help the driver to learn how to drive in the driver simulator, or we could make the policymakers to test their policy in advance in the simulator. So in the year of KDD 2020, we organized a competition on designing different quarantine strategies to contain the pandemic. The competitors proposed different strategies to decide whether a person can move freely or should be quarantined at home. So all their policies are tested on our simulator, the epidemic simulator. And the simulator provides a quantitative evaluation for them. So that I believe that the simulator work is necessary and promising in the future. And the learning to simulate problems, we also have a lot of publications already. Also in KDD 2021, we held a KDD Cup test, invite all these kind of competitors to test their decision-making policies in our simulator. And so speaking of learning to simulate or how to build a more realistic simulator, usually there are two methods, the heuristic-driven and data-driven methods. And the simulation could be formulated or could be generated into a problem of transition modeling. So given a state S at time t, we want to have a model to give us the next time step state. So in the next time step, we reuse this model and do the prediction for the next time step as well. So this is the transition modeling problem. It could be used in traffic, could be used in the weather, or it could be used in the crowd prediction. And usually these models people build are based on the heuristic-driven method. So the heuristic-driven method is like they have these physical models, like how cars speed up or how cars stopped, based on the human expert's knowledge. And this human expert built this physics model, and this model would be implemented in the simulator. So you can see that this model could be ideal, and there are some strong assumptions on the physics model. But the good thing is like it relies little on the data to calibrate this model, and because it's based on the human knowledge. And the data-driven method is sort of like we have a lot of data, and we learn this machine learning model from the data. But there is one problem with this data-driven method, which could be sometimes the data is biased or sparse, or the model cannot generalize because you are training on the biased or small data. So the good thing is like it has little assumptions on the form, but the bad thing is it needs to rely on the big data. So I'll give you an example on how these two methods works in the traffic simulator. So take the example of like vehicle movement simulation, and here, so the input for vehicle movement simulation is the vehicle positions in the past or in current situation, or its previous acceleration or deceleration situations in the past. And the output for this vehicle movement simulation is to output the positions in the future or for the new scenario. So, so a lot of factors have been influencing the vehicle movements, like the car following behavior, say how vehicles accelerate or decelerate based on your distance with your previous cars, or the lane changing behavior, how you change your lanes in order to get to your destination faster, or the routing behavior, how do you choose your routes? So here I'm gonna just talk about the car following behavior. So in learning in the car following behavior, so there are usually two approaches I mentioned, heuristic driven and data driven. So how does this heuristic driven method works? Usually the heuristic driven methods are called model calibration. The first step is definitely you assume a function of the car following model. So here the car following model taking the input as the distance to the previous vehicle, the speed of the leading vehicle, and the speed of the following vehicle. And the model have several parameters, which is the maximum speed allowed in this allow on the road, and the maximum acceleration or deceleration rate for the vehicles. These are already predefined parameters, and you want to tune it. And the output is the ideal speed for the next time step. So the next step, after you assume the function of the model, then the next step should be we define a measurement or distance function for your evaluation. So it's sort of like the loss function, but here we do not optimize them. And then the third step is we define the candidate parameters for the V here, the maximum speed, the acceleration of deceleration rate. And the fourth step is to fit into the existing data you have. And you choose the best parameters that it has the smallest distance. It's just simply search algorithm. Like you can use table search or other search methods to choose your best parameters. But you can see here, they have strong assumptions on the relationship between the parameters and features. And those things are not really held in the real world situations. But in contrast with this model calibration methods, as I mentioned, currently we have the data-driven method, the imitation learning method. The imitation learning methods are having like the behavior cloning or the generative adversarial imitation learning. So based on these two, the imitation data-driven method, you could have learned a realistic simulator. So after we know that we could learn the simulator and we could have learned them, but can we learn them now? So that motivates us to further take a step back to dive into this problem. So now that we have this data-driven model could help us learn more realistic simulators, can we learn them now? So as I mentioned before, the data-driven method rely on the big data, right? Ideally, we could have the big data. We could have as much data we want, as detailed as possible. This is a similar thing did in the game simulators or the robotics. They can log as much data as possible or as detailed as possible. But in reality, in the city, we could only have small data. The small data mentions maybe sometimes we do not have the direct observations on how many cars are on the road, or we do not have the trajectories of all the cars in the city. We only have sensors on certain areas. We do not have the observations for certain time steps, or we do not have the observations for certain places. So my group have been dealing with this learning with small data since I graduated from Penn State. So we also want to make sure this small data challenge is not just limited in the traffic scenario, right? So we want to make it a general problem. So we want to ask whether this small data is only happening in traffic, and the answer is no. Because say in healthcare, you can only log or you can only have the patient's data when they check in the hospital and when you examine them, right? So it's the small data it could happen in healthcare. Also in wireless network system, you can only have the locations of the users when they connected with your wireless network or they pass into your network. You are not of the full trajectory of them, right? So we believe that the small data is a really general challenge for currently AI or machine learning or data mining. So later in 2020, I sort of tackled the first challenge in learning the car following model with the sparse data. So here the setting is given an intersection, we only observe them when they enter the system or they pass into this intersection. It's mimicking the situation where we only have the roadside cameras along the intersection or along certain intersections. So here you can see the gray and red is the full trajectory of the vehicle, but we can only observe their actions or their states at the red dots when they're passing the traffic or passing the intersections. So knowing this setting, so how can we deal with this sparse data? So if you are familiar with sparse data or if you're familiar with the data imputation, usually the general idea, like people dealing with sparse data or sparse trajectory, is to do the imputation first. So imputation on the missing data usually requires the translation from the observed data. So you can see here, if I'm asking you to impute, giving you the 2 dots, I'm asking you to impute the trajectories. What you would do is like you would assume that the cars drives moving in a uniform speed, right? You would assume that the transitions from this dot to this dot is uniform. So you would have a uniform dot, right? So you can see that imputation on the missing data usually requires the transition functions from the observed data, right? And for the imputation model, you would require the observed data from the time t and time t minus 1 or previous time steps, and the output is the missing data at time t. But actually, the transition model should also require some information from the imputation model. So the input for the transition model is like the full data at time t, and the output is the full data at time t plus 1. So you can see that the transition model and the imputation model should be inherently one model. So based on this situation, in this ECML-PKDD paper, we propose that in using generative adversarial reinforcement learning to learn this car following model and the sparse data with an additional simple component interpolator to interpolate this trajectory. So usually I'll just give you a brief, like the process of how this model works. So usually we have the generator. This is similar to GANs, right? In GANs, we have generative adversarial network. We have a generator and we have a discriminator. So here we also have a generator. The generator is the model we want to learn, the car following model. So it's taking the state as input, output, and action, right? And then this action would be fitted into the simulator, and the simulator could give us a generated dense trajectory. This is a full trajectory. And in the real world, we have this expert trajectory, which is sparse, right? And in order to make this expert, this generated dense trajectory compatible to this expert trajectory, we need to downsample them, make this generated trajectory also sparse, right? And with this dense trajectory and this sparse trajectory, we can learn an interpolator here, right? The interpolator could interpolate the input sparse state into a dense generated state, right? And we can learn this part here. And with this learned interpolator, we could also make this expert state sparse output a dense expert state trajectory, right? So this is an interpolated sparse trajectory. And with this interpolated dense trajectory, we could use the discriminator to discriminate whether this is generated or it is from the expert trajectory, right? And then this discriminator, its output will be used as the reward for the generator. So this is the idea of basically under the framework of generative adversarial imitation learning. And I can give you an example on how this performs. So here, you already see this. We have this ground truth scenario where we only have observations outside of this gray area. And this is a traditional method. You can see that they move uniform in a uniform speed, right? But our method could learn the basically near realistic movements of the car's acceleration or deceleration, right? And we also conducted exhaustive experiments under different data sets. We have these ring road data set, and we have this single intersection data set, which is what we did here. And we also have these real world data sets. And you can see that with less than only 1% of the dense data, we could also have a good results on this final performance. So here is the root mean squared error measuring the time difference and the position difference. You can see that all those kind of data sets, our proposed method perform better than the heuristic-based method or the data-driven method without imputation. And I will give you a more detailed example on how this errors differentiate, which is each other in different methods. So here in this setting, we have a ring road where the vehicles are moving in this ring. And here we have this first vehicle and moving in this ring. And we have 4 cameras, and we only have the observations when the vehicles pass through the camera. So here the gray dots are the vehicle zero's full trajectory, but we only have 3 dots observations here. And you can see that the blue dots are our method. They can mimic the real world trajectories near perfectly, but the existing methods like the behavior cloning or generative adversarial imitation learning, those imitation learning methods and those calibration-based methods are not performed ideally. So this is what we did in this ECML-PKDD paper, which basically learns the car following models for under the sparse data. And so in simulation, in simulators, as I mentioned, the vehicle movement simulation is just one component. It's used in macroscopic model, but in traffic simulator, we could also have mesoscopic or macroscopic model. Like how does this our proposed method, like the learning with imputation, also benefits those macroscopic model or mesoscopic model in traffic space simulation? The answer is yes. So in this year's KDD, my student has been combining the interpolation with prediction, predicting the road level traffic states under the sparse data. So in this setting, we only have road set observations on those outside of this gray area. So we only have the observations in this 10, around this 10 intersections. And the traffic around the gray boxes here are totally unobserved. Usually in this case, like we cannot do any traffic control algorithm because we do not have observations here. So in this settings, our method would be combining the interpolation on traffic models with the deep learning models, and we do the predictions with interpolation. So this is the heat map on the errors around each intersection. So the greener, the better. The number is lower, the better. And so you can see that without the imputation, and you can see the whole network gives the larger error, the predictions on the error. And these with imputation, the whole network seems get greener, so that the lower errors. So after we have this answer this question on whether we could learn the realistic simulators now, so with combining with imputation, we are finally have this step to move forward. So we could have realistic simulators. Is reinforcement learning ready to be used? So my group had been answering this question in these 3 aspects. Definitely in previously we mentioned, you have to deal with the learning a realistic model under the small data. But in order to apply reinforcement learning in the real world, you could also have the small data challenge, right? So in the real world, you could also have missing or noisy data. How can we deal with that? The second challenge in reinforcement learning being used in the real world is like we need to have a trustworthy model. We need to guarantee that this model is safe and secure and robust to those noisy or missing data. And this last and the very important step is to how can we mitigate, even though our method training the simulator is not realistic, how can we directly mitigate the gap between the simulators and the real world throughout this model? So I'll just briefly go through our paper one by one. So one challenge by one challenge. So the small data here is like, as I mentioned in this example, we do not have sensors around those gray boxes here. So usually, if we do not have sensors in those areas, we cannot do any dynamic control because we do not know their traffic situations. So conventional practice in traffic signal control is just setting the fixed time for those intersections, say 30 seconds in this direction, 30 seconds in that direction, right? So it's no dynamic control. But with the imputation and model-based reinforcement learning, we can now finally enable these intersections with dynamic control. So here we have these evaluations on the average travel time for the for the different intersections. You can see that with the imputation and model-based reinforcement learning, our method can achieve a greener or lower average travel time for all the vehicles, for all the intersections. Oh, so this is here we are just dealing with the reinforcement learning and their sparse observation, right? But sometimes we do not have the real world observations at all. So how can we, or we cannot interact with the real world environment at all? How can we have a good reinforcement learning model? So usually people would do offline reinforcement learning instead of like directly push ourselves into this whole big area of offline reinforcement learning. My group have been investigating what makes the errors propagate in the process of learning the offline reinforcement learning model. So basically, we noticed that the offline reinforcement learning, usually if you have a offline data set, the first step is to do trajectory optimization. You want to learn a model that can predict or can mimic this data set. And then based on this mimic data set, you do the planning and learn this your final policy. So you can see that if your errors here is large, it will finally propagate through the final output of your policy, right? Propagation process, we notice that if your this H is the number of steps in your learned trajectory, if you're having a trajectory optimizer transformer or the trajectory optimizer better at the lower error, then the final state value function error could have smaller error. So we can prevent an increase in the final your policy error by learning a more precise trajectory model, and you can design your state or your actions to have a smaller action space so that your final policy could also have a smaller error. And then on the second challenge, the trustworthy model, we investigated the safetiness and the security of this of the deep reinforcement learning model. So if you're familiar with adversarial learning, you would know that this is a very general challenge for deep learning models, right? So, but in our previous method, we also use deep learning for reinforcement learning. So we are also wondering whether this deep reinforcement learning policies also be vulnerable to this adversarial attacks. So here in this example, we investigated whether a well-trained reinforcement learning model. So here in this left-hand side video, this is the open source model by OpenAI. They trained this blue robot to reach this destination as fast as possible with considerations into the block of the red robot. You can see that it can reach to its destination in a very, very efficient way. But with this well-trained model, open source by OpenAI, we train an adversary model or adversary policy that can give a simple, seems very odd position or gestures to trick the blue robot here, which is a well-trained model, to fail easily. So a well-trained, basically the idea is like a well-trained deep reinforcement model is vulnerable to these adversarial attacks. So we're saying we should further investigate the security of this reinforcement model in order to make it applicable in the real world. Also, we also care about the safetiness of this model. By safetiness, we're saying is reinforcement learning models their actions are safe in the environment. Are they making these dangerous actions to make the environment driving the environment into a dead end? And in this paper, which is just accepted by AAAI, so we proved that by integrating the safety model from transportation, it is guaranteed to have a superior performance than the existing reinforcement methods, while guaranteeing the safetiness. Okay, to basically summarize all my work, so my current work is sort of doing the trustworthy decision making. You've seen this figure before, and if we summarize this figure into a more into another dimension, here we could have these three analytics ranked in their difficulties and their value, and we have another dimension of automation. So we want these human to interfere with analytics as less as possible, but with descriptive analytics or predictive analytics, in order to make a final decision, we definitely need human input, right? Remember, we have this pedestrian recognition or this trajectory prediction. If we give that result directly to humans or to the models, we still need humans' input to make a decision. But prescriptive analytics can directly learn from this data and directly give the decision or recommendation. But there's a lot of challenges I mentioned. There should be safeness and there should be secure. And more importantly, it should have interpretability, understandable to humans, so that the humans can trust your decision. And I also mentioned that the trustworthy model should be considering the real world noisy and missing data into their learning process. And the long-term vision of my group is trying to build a actionable decision-making from trustworthy. So the difference between actionable to trustworthy is that, like here we can see that the prescriptive analytics still gives you the decision, even though this analytics give you the decision or the recommendations, you still need to train it in the simulator. You cannot, or you need some guarantees to make them directly applied in the real world. So either you trust yourself, like trust the guts, you do the boat trial from your the output of your prescriptive analytics model into the real world, or you want to the sim to real transfer. There is a guarantee that the gap, even though there is gap between simulation and real world, you can still learn, you can still have better performance. You need to do that to do the guarantee on the sim to real transfer as well. So this is a long-term vision of our group to do the actionable decision making in the real world. So we have a bunch of papers published already dealing with the data, dealing with the model. We also do a lot of build a lot of simulators. And this year, our paper on building a realistic simulator for the traffic signals and for a game environment is also accepted by NeurIPS. And I'd like to thank my my collaborators and my students for this, and NSF and Department of Energy for funding our research. And in the very end of my talk, I would like to give a little bit of advertisement. So this year at AAAI, we have a workshop on deep learning hardware co-design for AI acceleration workshop. So we are still in the phase of call for papers. If you have any paper related to AI acceleration, so please consider submitting it. And we also have a general call for submission in transportation systems. Also, as I mentioned to Tyler, I'll be at NeurIPS this year and presenting our simulator on reinforcement learning generation. So if you're here, feel free to come by. And that is all for my talk. Any questions?
Thanks.
Fantastic. Thank you so much, Or.
Thank you, Sophia.
So are there any questions from the audience? If not, maybe I can start with one. So in the adversarial attacks to reinforcement learning agents, right? Are there any assumptions that the attacker knows about the type of defenses that the RL agents has? So is the attacker essentially a generic attacker, or is it oblivious to defenses? Or has there been any defenses on the RL side, right? Like, so I missed that part.
Yes.
Are we using like adversarial training to avoid these attacks in the RL setting?
Yeah, you're making a really good point and asking a really important question here. So here, the attack here could be conducted in white box or gray box or black box. We do not need to know the weight for the blue robot here. We do not need to know their weight. All we need to know is their observations. If we know their observations, and we do not need to have the direct access to their modifying their observation. We just need to know their observation. So this is the assumption. We do not need to know their model. We do not need to have the access to modify their observation. We just need their observations and to know that we, like the red human here, the red bot here, its gesture is in the observations of the blue robots. So we can tweak ourselves, make ourselves an adversarial sample for these blue robots. That's the assumption. And about the defense, actually, we noticed in our recent paper, we noticed that this simply training a policy, like training a red robot here for the blue dots and adding it as a sort of like a adversarial sample for the blue dots retraining is not enough. So it's we sometimes I think the challenge is because if you fix your opponent in multi-agent reinforcement learning, if you fix your opponent of the red robot here, and you train a policy that purely against it, and then your final performance will not be guaranteed to generalize to other agents. So if you have only one adversarial policy trained for this blue robots, it will not guarantee the blue robot will not perform better than other like general agents. So that is the challenge for multi-agent reinforcement learning. So the adversarial sample is not guaranteed to be the adversarial sample for other reinforcement learning agents. And speaking of the to making it to defense against it, one possible way is you have a bunch of reinforcement learning agents along the way. You do not just train against this red robot. You train against yourself, and you train against your historical models, and you do the population training. You just not train against one sample. Does that answer your question?
Yeah, absolutely. So, I mean, thank you for clarifying that. So just a follow-up then, right? If you're using reinforcement learning to, for example, control the traffic lights, right? Knowing that there is a possibility of attack, there is a possibility of out of distribution, like the data that we are observing might be completely out of distribution for this RL agent, or for whatever reason, right? So what are the safety nets in place to ensure that the RL agency is not making a decision that leads to some catastrophe?
So I can clarify on this, like what did the safeness here mean. So in this paper, we as human, we learn how to drive. We know there are some safety rules in our driving, right? We have this driver's test. We know what are the rules, but the traffic signals, they do not, when they learn it, they do not know that. Say, for example, we want to make sure these vehicles turning left are yielding to these vehicles going straight or turning right. So how can we do that how can we guarantee that in the learning process? That is what we do here. So here we are saying if you want to make the traffic the intersection safe or collision free, you need to consider this traffic rules in our human. So in this work, we have been asking this traffic engineers a lot of times to ask them whether what is the ideal or what is there a general form of the safety rules, and they help us to build a safety rules from the driver's manual in New Jersey, so that we can finally formulate this traffic rules that can be integratable in this reinforcement learning agents. Does that answer your question? So in order, so the safety net here is basically to guarantee the cars are not conflicting with each other in the intersection.
Right. So that feasible space, is it well defined? Right. Like, so there is a feasible, there is a safe set of actions, right? Like,
yes. In order to the safe set of the actions, they are giving they're giving some rights to the mobility, right? So if you are having a definitely safe set, then the cars are not moving at all, right? If no cars are moving, then that's definitely safe. So, but here you can see that in this figure, we not only consider the safetiness, the number of collisions, we also consider the average waiting time. So we also want to optimize the mobility. We want to guarantee the safetiness as well as we have all the cars moving faster in the road.
Thank you so much. This is really fascinating. Thank you. Yep.
Yeah. Thank you for the question.
Any other questions? So one I had was with the works for the imputing the dense data from the sparse traffic data. And so it looked like that was heavily based on the quality of the simulators. So going from the sparse data to then impute this dense version of the data.
Yeah. So you're right. So as I mentioned earlier, the traffic simulators, they are having a lot of in order to simulate the traffic, the vehicle simulation, there are a lot of different models or behavior models that can influence the final performance, right? So the car following behavior, lane changing behavior, routing behavior. In our paper, in ECML-PKDD paper, we only optimize the car following behavior, and the lane changing and routing behavior, we are keeping them fixed. So we are trying to sort of optimizing them as much as possible, even though we know that the lane changing behavior or the routing behavior, they could be unrealistic in this situation. I believe that future work could be jointly optimizing those lane changing and routing behaviors, because I think it's also doable, because this is what people do in model calibration. They calibrate the three models altogether, and similarly, we can also learn these simulators altogether.
Okay.
Right, because the laws could be used to guide not only just one simulator, but also used to get three simulators. But definitely the challenge here is how can we assign all those kind of rewards or the losses to different generators. I believe that is really good work in the future.
Okay, and this is also a current or future direction you mentioned, because I think at the end you mentioned also, with the works in the direction of the simulators. So that's pretty exciting.
Yeah.
Okay. I guess another question is, if you can maybe highlight for us some of the key challenges that you think in this reality gap of going from these works kind of in academia and in simulation and bringing that to the real world. That if you can maybe summarize some of these challenges.
Yes. So here I briefly introduced the two. So we know that is a reality gap, right? But the first thing we want to know to tackle this challenge is definitely we want to quantify the reality gap or benchmarking this gap. So in the traffic signal control domain, we have the traffic simulator and we have the real world data. And we have the controllers in training simulator. and controllers that would be applied in the real world. We definitely need to quantify how much is the gap. We cannot do any optimization unless we have this quantification. So that's the first step I believe that is need to do. We also have this paper that in traffic control or in other domains, if you have two simulators, you can do instead of doing sim to real transfer, you can first do sim to sim transfer, right? You can transfer from one simulator to another simulator. So that could be one simulator could be considered as a simulator, and the other simulator could be considered as reality. So you quantify the gap between them, and hopefully that could be giving you a signal on how, or at least you can train it in a simulators. So that is the first step. You have the quantifications on the gap. And the second step is definitely bridging over the gap. That is a very general topic. Like recently, the sim to real transfer has a lot of papers on like domain randomization or inverse model prediction or something. They have this invariant inverse model prediction. They have this sim to real transfer. They all claim to be the sim to real transfer tackling this challenge. I believe that is the good thing to do. But before that, we definitely need to quantify the gap before we do the mitigation between them.
Yeah, like you had mentioned, the simulator to simulator types of things.
Yeah.
Okay. Well, really cool.
Yep. Thank you for the question.
Well, I guess if we don't have any more questions, really great presentation, and we really appreciate your time for giving the talk today.
Thank you guys for having me. I really enjoyed it.
Yep. Thank you all. Thank you, everyone.
Okay.
Bye.